In this video, I'd like to take a look at how we can use or why we can use the normal distribution to approximate the binomial distribution. And so we're gonna play around with this Excel file and see how well the normal can do to approximate the binomial. So at the end of chapter 6, we turned our attention to the binomial and used it to describe a whole host of different possible experiments in our world. Here I have this set up to think about, again, that free throw example. And so we can model this and we can look at the likelihood of making a certain amount of shots. So we walked through 5 free throw attempts, and you probably even recognize some of these numbers. You know, the chance of making 0 all the way to 5, and this was our binomial probability distribution that we built. Now, I do have this set up. We can change the likelihood of making a shot. So if we want to think about a 45% free throw shooter, it'll auto update over here, right? And you can so we can build that. We've done that, right? We did that in a previous file, but that would include doing the whole combinations formula and whatnot. Okay, so another thing to notice is that Excel can do this for us, and there's in fact a binomial distribution function. So if you use the binom.dist, and you can kind of follow along and take a peek at what I have done here, but really what it needs is the following input. So of course you need to tell it how many you would like to make. So this A10 is I'd like to make 0. You need to know how many shots you're taking. So H1 is 5 attempts. And then we need to know the probability of making each shot, right? And of course this is following the assumptions of the binomial distribution that every shot is still a 45% chance. And then here we want to this function can do more than just what we're asking it to. So you do need to have false in here. You want the value at just that precise at 0. So if we put in true, it would do a cumulative function, which we may sometimes want. So we can do that. That kind of bypasses a little bit of the grossness of calculating this, right? We don't have to necessarily run the combinations formula like I have set up over here, right? So in the past we walked through building that, but we don't need to do that. So yeah, so we can build that binomial probability distribution, and again with 5 shots, so 6 possible outcomes, it's not that cumbersome. So there's more going on here in this sheet that you can peek around at. We won't go through everything, but we can calculate the mean in a couple different ways. So we can do it directly from the table that we have built here, or we can do it theoretically with our handy binomial probability formulas, right? And so this is simply n times pi gives us the mean, and we can see that actually checks out as the mean of this table over here. So yeah, actually this column, right? So this is x times px, which is our way of summarizing or taking the mean of a distribution, as we can see over here. Okay, so we can go about it either way. So this is kind of out of order, but these two are related to doing it in this box, and then down here the mean and variance of binomial we can do directly up here. So just highlighting, you can take a peek that both of these work. It's just that the binomial formulas are a little more simple. So that's not really the heart of what I wanted to show here. What I want to show is the binomial again, and using the normal to approximate. So I have plotted down here the probability distribution, and we've seen these orange boxes or something similar to it when we built them on our own, and And of course, this is going to change, and you probably recognize it better as the 0.7. This is what we originally built. Okay, so we can already see that in some sense. So I've overlaid a normal distribution or normal curve on top of it, and you can see how there's not a real clean way to do it in Excel to put a normal distribution, or maybe there is, and one of you knows it and would tell me, but it takes a little cumbersome calculation. So I have that built down here if you're curious as to what's happening. Overlaying it on here, we can see that already with just 5 attempts, the normal curve kind of fits it not horribly badly. And in fact, if we go ahead and look at, for instance, if we crunch the numbers with the binomial, and we want to know, for instance, greater than or equal to x. So what's the chance that you make 3 or more free throw attempts? So 3, 4, or 5, and we can find that again with some Excel formulas. This is a much more complicated formula, so you can try to dissect it if you want, and might give you some insight. But what you need to know is that this is grabbing 3, 4, and 5, and so again, you could verify that by just adding these up, right? That's what, 66 plus 16, that's 82. With that is going to be 83 something. So yeah, so the total likelihood that you make 3, 4, or 5 in this case is 83%. Again, this is going to update if you're a 45% shooter. You have a much less chance of making 3 or more. And we can turn that into anything. Maybe you want to be a 13% shooter. So yeah, and we can also change, and maybe we want to think about 2. Okay, and that's also going to update. And so we would see the total of 2 through 5 being 96%. Okay, so just some things you can play around with. So mainly on this sheet, the best you want to restrict yourself to changing the pi up here, and you can change this x here. If you start changing other things, you might lose track of, or things might start to break down. Now that I encourage you to do that. You can always re-download the file from Canvas, or when you download it, go ahead and save it as a new file, or as we talked about, you can go ahead and make a copy of the sheet. That's another solution. Okay, so this is the binomial method, right? And this is the real value of the binomial, 83%, for instance, okay? Now, that means that there's a 16% chance of being less than, right? That's just the total percent likelihood, right? If there's, well, we're not into normals yet, but if 83 are greater than or equal to, then the remaining 16 is the complement. Now, what I have down below is, what if we just went ahead and used the normal to approximate? Okay, and so we can use, again, just like there is a binomial distribution function, there is a normal distribution function. And so let's take a break and just come on over here, and we can see that there is, pull it up here, this is the norm.dist, so normal distribution function. And again, what I'm plugging in here, I'm just showing you in this little box how this works. We can plug in the value that we're interested in. So maybe we're interested in 24. Excel then wants to know the mean and the standard deviation, right? That's the important 2 items to describe a normal distribution. And then here we do want the cumulative distribution, right? So when we're working with a continuous distribution like the normal distribution, we need to worry about the cumulative value there. Otherwise, we're just going to get that pinpoint value, which again might be interesting, but that's going to give you just the height at that precise location. Okay, so we are more interested in the total. So let me put true back in there, and what we get is 84%. So this is just in this little situation here, and that should feel familiar. I can change X here, and we're going to get 16% or just under 16%. Right, so this is 1 standard deviation below the mean. And what this means, now this is a little bit different than the z-table. Okay, so what Excel's normal distribution function always measures is all the way to the low end. So if I pick, for instance, here I have 16, we have a mean of 20. Excel is going to measure this area and give us the information that that's 15.8%. Okay, so this is different than the z-table. The z-table would have returned, basically this. It would have given us this, which we know is equivalent to this area, and we'd have to do a little math on our own. So it's important to know what Excel is doing and what the z-table is doing, and they're doing slightly different things, but we can get to the same results. So every time we plug this into, if I change this to 24, again we're getting 84, and that's because Excel is giving us all of this area, right? So it's not doing that, cutting it at 50% like the z-table does. So just be aware of that if you ever try to use Excel to kind of speed up your process or work with normals. So we can find the normal distribution and the likelihood of being less than a certain value. Now, of course, we can adjust that, or we can use that, the fact that Excel is going all the way to the bottom. For instance, if I'm interested in, maybe I'm actually interested in the between these two, right? So between 16 and 24. Much like with the z-table, we could do some manipulation and find that out. Here I can do, let me just plug in another one. Let's do the norm.dist, and I need X. I'm interested in the 16, the mean, and the standard deviation, and we do want that to be cumulative. And so this is going to pop up that 15 point something %. And now, just like we do with the z-table, we kind of subtract off or add together what we need. Here, if we do the larger one minus the smaller one, we're going to get that 68%. And that should be, you should start to kind of expect those results if we see something that's, this is 1 standard deviation above, and this is 1 standard deviation below. And so what do we find? We find 68%, right? Empirical formula in action here. Okay, so in some ways, or I would say the Excel norm distribution function is a little easier or more intuitive than even the z-table. But as long as you keep track of whatever the method that you're using, whatever it's telling you, and again, this is why I encourage you to get in the habit of drawing the little pictures to help yourself remember. They both can work. So with all that said, so we have the norm distribution function at our disposal, and so we can turn and use that to estimate the binomial. Okay, and so what I have here, I have the likelihood of being less than a certain value. Okay, so I again am plugging in 3. I'm giving Excel the mean and the standard deviation of the function, and yeah, so we can do that, and what we get is 31%. So we have a little issue here, and we can maybe start to see that visually in that when I choose, if I'm interested in 3, 4, or 5, right? That's what I'm actually interested in here. Is greater than or equal to x. So that includes 3. I don't know if that shows up that I'm highlighting that. 3, 4, and 5. So all 3 of these boxes I'm interested in, right? That whole probability is included. But when we think about the normal distribution, if I choose 3, I get a value, and I'm just going to guess where. Nope, that's not where I want to be. Let's see if I can. Whoop. Okay. So I get a value that, or the 3, get rid of those. The 3 starts at this point and shades, whoops, and shades all of this area. Okay, but notice we've missed this value, or yep, that's too wide. We've missed the rest of this box, right? Actually, it goes up to here. All of this is gone. It's not included in our normal calculation. So the binomial correction factor deals with that issue. And so what it means is that when we think about 3, if we want 3 or greater, we're going to bring with 2.5 and greater when we deal with the normal distribution. Okay, so we're going to include 2.5 in our greater than portion, which the way I have it set up, because Excel's function thinks about less than, we go about it a little bit different. But you can see I'm subtracting off that 0.5. So we're still using 3 as our cutoff, but we're taking off 0.5. So really, Excel plugs in 2.5 into this normal distribution. And that's how we get around the issue that the normal distribution starts right at that value of 3, whereas again the binomial basically takes up all that space from 2.5 to 3.5. Really, the value of 3 is from 2.5 to 3.5, at least on the normal distribution. So when we plug that in, when we use that correction factor, notice what happens. We get almost exactly the value that we did up here with the binomial calculation. And that's really the takeaway, is that when we use the correction factor, we get a very close approximation. And this holds true. I can go up here and change this, to 12% free throw shooter. Again, we get a pretty good. Now, when we kind of are on the extremes, when we have a really, say for instance, a really bad and a really good free throw shooter, or a really good free throw shooter, the extreme ends, it gets a little tougher to get a really nice clean fit. So it does struggle a bit when you have a small number. So here we're only shooting 5 free throws, and we're kind of on the extremes. But as we'll see here in a minute, it gets even better as n increases. As we take more shots, the normal becomes better at approximation. So let me go back away from the extremes here and into something that's at least close in our case. So even by the now we're 30% free throw shooter. I guess that's kind of the flip side. Yeah, so we're still off a little bit at say 19%, but we still do much better than if we don't make that correction. Okay, so you can kind of play around and compare how well we're doing, and you can see the fit. The fit is not quite as nice on these more extreme cases. So yeah, let's go ahead. We're gonna now pretend we're gonna shoot 30 shots instead of 5. So I'm flipping over to this new sheet, and similar setup. Okay, the tables just get a little bigger, and we can play around with the percent as well. And here again, we see the correction factor doing pretty well. Here I'm thinking about making 23 out of 70 shots. And yeah, so without that correction factor, we struggle a bit more. But when we put in that correction factor, we do pretty well. We can play around with that as well. We can see again, even visually, the normal fits this curve quite nicely. So again, as n increases, we do better and better with the approximation, and we can take that all the way out to 90 or more shots. And so in this third sheet, you can see how nicely it fits here, and how close we are here. So we're off by 100th or 1,000th of a, well, I guess 1/10%, but yeah, so 77.3%. If we ran this analysis, we'd say, oh, you're going to make 33 out of your 90 shots 77% of the time, or 77.3, and in reality, we would say, if we use the approximation, that you'd make it 77.4% of the time, when in reality you make it 77.3%. Okay, so as long as you don't, for some reason, need extreme precision, this is a quite good approximation. And one of the keys here is that this is it's a simpler it's computationally easier. And so again, nowadays we can, even for this situation, obviously we can just plug in binomial calculations or binomial distributions. But again, the process is a little more cumbersome even here in Excel, even in this day and age. So it's still easier to just go ahead and assume that it's a normal, or approximate it with a normal, and we can see how normal it gets, even when we we're on more of the extreme ends. My curve has gotten a little, I think my putting these both on the same graph is getting a little wonky here, but it fits nicely. It's just not yeah, we can see that. So we're kind of on the extreme end here. We're at a 10% free throw shooter, but notice, because n has gotten bigger, we're still doing a pretty good job at approximating. Okay, it's not off as much as it was when we were dealing with just 5 shots. So we can go back to what my scales worked at. So I think I have an issue with putting both of these. Remember, the normal distribution is coming from this funky calculation here, and I have to put it on a second scale. There's kind of a hidden y-axis over here. So I got some issue, that some bug that is not playing well with my normal distribution. But you can see here, at least in this case, how well that fits the distribution. So yeah, so what I'm trying to highlight here is that we can use the binomial to relatively good effect to approximate the, I think I said that wrong. We can use the normal to approximate the binomial distribution. And again, that carries with it some computational ease and an ability to do some more kind of complicated statistics, or more advanced statistics, or methods that we'll turn to in the next few chapters. So we can use binomial experiments and still apply some of our techniques in later chapters. Yeah, so again, this is going to be posted to Canvas, so you can get in there and play around with it. Don't feel like you have to spend a lot of time on it if you're busy reading binomial distributions anyway. Yeah, I wanted to make that available so you can see the normal, and yeah, just see some other things that Excel can do. So if you're interested in Excel, go ahead and take a look at some of these methods that I use here, the sum index, the table stuff, and know that you might find an easier way to do it. And if you do, you should let me know. Yeah, so we'll leave it there. Yeah, hopefully this helps kind of incorporate that concept.